Through various experiments, it was established that an atom consists of subatomic particles such as protons, electrons, and neutrons. Now, let us look at the arrangement of these subatomic particles in an atom. Different models were proposed to explain the distribution of subatomic particles in an atom. Of these models, the models proposed by J.J. Thomson and Ernest Rutherford are of great significance as they paved the way for modern structure of an atom. Let's discuss both these models one by one. J.J. Thomson, in 1898, proposed the atomic model called Thomson's atomic model soon after the discovery of electrons. According to this model, an atom is a sphere of radius 10 to the power minus 10 meter with uniform distribution of mass and positive charge, with negatively charged particles called electrons embedded in it. In this model, the negatively charged particles that are embedded in evenly spread positive charge can be visualized as plums or raisins or seeds that are embedded in a pudding or watermelon. Therefore, this model is also called plum pudding, raisin pudding, or watermelon model. Although this model successfully explained the overall neutrality of the atom, it could not explain the results of the scattering experiment conducted by Ernest Rutherford. Also, it couldn't explain the stability of an atom. That is, how the positively charged particles are shielded from the negatively charged particles without getting neutralized. In order to validate Thomson's atomic model, in 1911, Rutherford and his students, Hans Geiger and Ernest Marsden, conducted an experiment called the gold foil experiment or alpha particle scattering experiment. Before we proceed to alpha particle scattering experiment, let us acquaint ourselves with the term alpha particle. Its source, other particles emitted from the same source, and their few characteristics. We know that certain elements emit radiation on their own, and this phenomenon is called radioactivity. The elements are known as radioactive elements. The alpha rays are emitted by these radioactive elements along with beta and gamma rays. Rutherford found that alpha rays consist of high-energy particles carrying 2 units of positive charge and 4 units of atomic mass. Hence, these particles are dye-positive helium nuclei. The beta rays are negatively charged particles similar to electrons. And the gamma rays are high-energy radiations like X-rays. Unlike alpha and beta rays, gamma rays do not contain particles and are neutral in nature. The alpha particles have the least penetrating power among the 3. The penetrating power of beta particles is nearly 100 times and the penetrating power of gamma rays is 1000 times more than that of the alpha particles. Now let us move on to alpha particle scattering experiment. In this experiment, a stream of high-energy alpha particles from a radioactive source was bombarded on a very thin gold foil. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the zinc sulfide screen, a tiny flash of light was produced at that point. If Thomson's model is correct, then all the alpha particles should pass through the gold foil almost undeflected. This is because the entire mass and positive charge is uniformly spread throughout an atom. However, the observations were quite contrary to these expectations. The following are the unexpected observations made in this experiment. Most of the alpha particles passed through the gold foil undeflected. A small fraction of the alpha particles were deflected by small angles. A few alpha particles were deflected by large angles. A very little amount of alpha particles, 1 in 20,000, were bounced back to the source, that is nearly by 180 degrees. Based on these observations, Rutherford concluded that as most of the alpha particles passed undeflected, most of the space inside the atom is empty. Only a small number of deflected particles suggested that the positive charge of the atom is not spread throughout the atom, as Thomson had presumed. Rather, it is concentrated at the center in a very small volume. The alpha particles that are deflected by larger angles and by 180 degrees indicated that the atom has a dense, positive charge with entire mass concentrated at the center. As the alpha particles approach much nearer to the massive positively charged center, they get deflected by larger angles, and as they directly hit the massive positively charged center, they get deflected nearly by 180 degrees. It is due to the increase in enormous repulsive forces from the massive positively charged center. Rutherford named the positively charged center present in an atom as nucleus. Calculations by Rutherford showed that the volume of the nucleus is negligible as compared to the total volume of the atom. For an atom of radius 10 to the power minus 10 meter, the radius of the nucleus is about 10 to the power minus 15 meter. That means, if a cricket ball represents a nucleus, the radius of the atom would be about 5 kilometers. Based on the observations and conclusions of the gold foil experiment, Rutherford proposed a new atomic model called Rutherford's nuclear model of atom immediately after the discovery of protons. According to the Rutherford's nuclear model of atom consists of a tiny, dense, positively charged center called nucleus. Entire positive charge and most of the atomic mass of an atom is concentrated in the nucleus. Electrons are found outside the nucleus. They revolve around the nucleus with high velocities in circular paths so as to counterbalance the electrostatic forces of attraction between the protons and electrons. Electrostatic forces of attraction hold the electrons and the nucleus together in an atom. As electrons move in circular paths around the nucleus, just like planets revolve around the sun in the solar system, Rutherford's atomic model is also called planetary model. Thus, Rutherford's model could account for the presence of nucleus and electrons outside the nucleus. However, it failed to explain the stability of an atom. According to the Maxwell's theory of electromagnetic radiation, a charged particle in circular motion emits energy continuously. Hence, an electron revolving round the nucleus also loses energy. As a consequence of this, the electron follows the spiral path towards the nucleus, and this ultimately results in collapse of an atom.